Okay, let's give this another try. What are we doing? We're going to solve now a system of 3 by 3 using elimination. Okay, and remember we're going to keep all our variables in one equation, eliminate one variable from another equation and two variables from the third equation so that we can then back substitute to find all of the values, okay, of all the variables. How are we going to do that? With three principles. Multiply an equation by any equation by a non-zero constant on both sides. We could interchange the positions of the equations, or we can add a non-zero multiple of one equation to another equation. I was in the middle of doing that when the last video ran out on me. And I was messing it up. So let's recall what's going on. So we were multiplying a -3 times this bottom equation to get minus 3x plus 12y equals a positive 3. And then so that is a non-zero multiple of the original equation. And now I'm adding that non-zero multiple to the other equation. So this is something that you've done before. And then of course you solve for y and plug back in for x. It's just now we're going to do it in a little bit, with three variables and three equations instead. Okay. Now you can do these in any order, okay? But these principles, but what we're going to do is we're going to consider the system two equations at a time, right? There's three, but we're going to do two at a time. All right. So let's go back to our original system. Equation 1 is x minus 2y minus z equals 1. Equation 2 is minus x plus 3y plus 3z equals 4. And equation 3 is 2x minus 3y plus z equals 10. Okay, so I'm going to consider them two at a time. Let's look at equations 1 and 2, right? If I add those together, the x is going to eliminate. That's the same thing as taking a multiple of 1, 1 times that top equation or the second one and adding it together, okay? So if we take equation 1 and 2, x minus 2y minus z equals 1 and minus x plus 3y plus 3z equals 4 and add them together, we get y plus 2z is equal to 5. Now what's going to happen is that this equation is going to replace our equation 2. So it becomes a new equation number 2. Why does that work? Well, every equation in a system of equations is expressing some relationship between x, y, or z, right? We still have the same relationship, so this one is still part of the system. And remember, what we're trying to do is find the values that have that relationship. Okay, so we have now accomplished our first goal, which is to eliminate the one variable from one equation. So we end up with y plus 2z equals 5 as equation number 2, and we still have the same equation numbers 1 and 3. Okay, so now what we're going to do is we're going to look at equation 3, and we need to eliminate the same variable that we just eliminated from number 2, x, and we're going to do another variable, and it could be either y or z, but I'm going to do y. Okay? All right. How are we going to do that? Well, if we consider equations 1 and 3 as a system, and we think about how we could eliminate, pardon me. We need to eliminate the x, but also the y. Right. I'm sorry. So if we wanted to eliminate the x, right, I could multiply this first equation by -2 and then add them together. So I get minus 2x plus 4y plus 2z equals a -2. And we keep the second equation, the third equation, 2x minus 3y plus z equals 10. The x's eliminate, and we're left with y plus z plus 3z is equal to 8, right? This is going to become our new equation 3. So we'll have equation 1, which is x minus 2y minus z equals 1. Equation 2 now is y plus 2z equals 5. And equation 3 is y plus 3z equals 5. Equals 8. Remember what we're going to do though, we're going to eliminate y, right? So how do we do that? Well, if we consider now 2 and 3 together, and we multiply one of them by a -1, let's multiply the second one by a -1, it doesn't really matter in this case, then we can eliminate the y. So we get y plus 2z equals 5, and we get minus y minus 3z equals a negative 8. And that gives us that minus z equals minus 3, which is true then that z is 3. Okay? So, we've now made our system into this. Equation 1 stays the same. X minus 2y minus z equals 1. Equation 2 has changed to y plus 2z equals 5. And equation 3 is now that z equals 3, right? Doesn't this look like what we were headed toward, right? What it looked like when I said if the system could have, some terms removed from it, it would be really easy to solve. Why, yes, now we can use back substitution, right? So we already know that z is 3. That's one part of our answer. So now I know if I take the z and plug it into the second equation, y plus 2 times 3 equals 5, I can solve this for y, and we get -1. And then if I take y and z and plug them into that first equation, I can find x. So x plus 2 minus 3 equals 1, and it turns out that x is 2. All right, those are the same 3 solutions that we got the last time. We could check it again to see if it works to plug them all in. All right, I'm going to show you one more thing about this section, and it's called curve fitting. There's one homework problem about this in this section and also one in 11.2 that you have to do. Okay. So what we're going to do is we're going to find real numbers, a, b, and c, so that the graph of an equation, y equals ax squared plus bx plus c, a quadratic equation, so it will be a parabola, contains the points -1, -2, 1, -4, and 2, 4. Well, we call this curve fitting because we're trying to fit a curve to some certain, parameters. Okay, so let's kind of sketch this out just to see what we're looking at. Here's -1, -2, and then we also have 1, -4, and 2, +4. Okay, so if I were to draw a parabola, and I don't know where the vertex is, but I do know that it goes through these 3 points, we're basically looking for an equation for something like this. The vertex could be a lot lower, but I'm not sure. Okay, so how are we going to do that? Well, each point that's given to us are coordinates of points on the graph, right? And we know that points on the graph satisfy the equation, right? Our equation is y equals ax squared plus bx plus c. Okay, so what we're going to do then is we're going to set up a system, and I'm going to use each point. So how about -1, -2 first, then 1, -4, and then 2, 4, to create 3 equations with 3 variables, right? So the first coordinate is an x and the second is a y. And in my equation I have x here and y right here. So the first equation is going to be -2 equals a times -1 squared. So notice what I'm doing. I'm plugging y and x into this equation here. Plus b times -1 plus c. Right? The second equation will be -4 is a times 1 squared plus b times 1 plus c, and the third equation is 4 equals a times 2 squared plus b times 2 plus c, right? And then when we simplify those equations, we get the system negative 2 equals a minus b plus c, negative 4 equals a plus b plus c, and number 3 is 4 equals 4a plus 2b plus c. So notice we've created a system in 3 variables, yeah, that are a, b, and c, right? So the coefficients this time become our variables, right? I'll let you solve this as an exercise, maybe using substitution or elimination as we did above, but the solution is that a equals 3, b equals negative 1, and c equals negative 6, right? So that means that our equation is 3x squared minus x, because it's minus 1x, minus 6, right? Let's take a look at the graph of this in Desmos and see if it really does go through those 3 points. Okay, I'm going to pause it, although you probably won't even recognize it because it'll come right back on. Okay, here we are in Desmos. I've put in the 3x squared minus x minus 6, and I'm going to move my screen or the graph over so that we can also take a look at it. Okay, now remember what the points were that we wanted to find. We wanted to find, or that we wanted it to have. Negative 1, negative 2. Negative 1, negative 2. Looks like we've got that right here. Yeah. Okay. Then the next one was 1, negative 4. Looks like we've got that right here. Yep. And 2, 4. Good. So that parabola actually does go through these points.